Good morning. Today we're going to present the article entitled Mathematical Modeling of the Output Power in Power Amplifier by Luis Surukawa and Eduardo Lima. This presentation will start with an introduction about radio frequency power amplifier. In section 2, a brief review about behavior modeling of power amplifier, explaining the bandpass and low-pass system. In section 3, we apply a studied behavior model to find our own model. In section 4, we present the results based on simulation. Following, we analyze the results. And finally, we show the acknowledgement. Introduction. The radio frequency power amplifier needs to be efficient and present a linear behavior. To do that, it's essential a model that at the same time runs fast and does not compromise its accuracy. In this article, we'll be using a black box system to model the behavior of the power amplifier. This approach focuses on the input and the output of the system, and does not concern about physical details or what's inside the box. We have studied two models, bandpass and low-pass. The first is simpler, use only real numbers. The second is more advanced, and use complex numbers, but it's faster than the first one because it adopts a lower sampling frequency, resulting in a better method to implement your model. Usually, it's the output that is modeled, but recently the output power started to be modeled, a value much more important and relevant to the project and study of a power amplifier. Behavior modeling of power amplifier. A behavior modeling proposes a way to get the output of the system from a database of input and output. First, the model will be trained with the data, and after that, the model will be able to estimate the output for every input, even those new. First, we need to model the output of the system, and to do that, we use a real memory polynomial model, defined as follows, where y is the predicted output, x is the input, p0 is the polynomial order truncation, m is the memory order, and a small p, m are the constants that will be calculated in the training. Working with the NP equation, we can find the output by two different methods, bandpass system and low-pass system. Beginning with a bandpass system, where we are working with only real numbers. Let's suppose the real input is a sine wave, represented in equation 2. We can use the MP model where m equals 0 and p0 equals 3 to predict intermediated output as presented in equation 3. Working with 2 and 3 and after the impedance matching, we are able to find the real output as shown in equation 4. The second method is the low-pass system, where we'll be working not only real numbers, but also complex numbers. In this method, we'll have in the following new complex input and complex output, equivalent to the real input and real output, where tilde x is the complex input, tilde y is the complex output, e is the Euler's number, and j is the imaginary unit. We can relate the real and complex signal with the equation 7 and 8. Finally, working with 5, 6, 7, and 8, we can arrive at the same conclusion by the bandpass system. This was an example where p0 equals 3 and m equals 0. But this relation between the bandpass system and the low-pass system is valid independent of the parameter chosen, given some minor adaptation. The real MP model can be adapted to the complex MP model, defined in equation 9, where p is the polynomial order. Finally, the relation between the polynomial order p and its truncated form, p0, is given as follows. In this article, we'll be using the low-pass method because it will be more efficient. Because the real input depends on the omega, that will be in the order of, and to respect the Nyquist-Shannon sampling theorem, the lowest frequency will need a lower sample rate, running faster the simulation. Output power modeling. In general, a PA model tries to predict the output based on the input, and if you need the output power, first you'll need to get the output signal and then calculate its power. Our goal is to find a power amplifier model capable of predicting the output power based only on the input data. To do that, we will need to apply the MP model to find the output in function of the input, and then applying to the power formula. where P is the output power and tilde Y to the power C represents its complex conjugated. Note that we are considering the resistance equal to 1 ohm. For P up to 3 and any value of n, we found our model equation, where P st is the output power estimated, and A, B, C, and so on are the complex constants. The reason why we decided to stop when P equals 3 was the complexity of the model. Where P equals 3 and M equal 1, we have an output of 6 elements and an estimated power of 36 elements. When P equals 4 and M equals 1, we would have an output of 8 elements and an estimated power of 64 elements, and it would take much longer to calculate it, organize, and generalize. Results. In this section, we simulated the model using MATLAB. We'll use the data collected from a power amplifier in gallium nitride technology, class AB. We used a Rhodes-Schwarz vector signal analyzer having the sampling frequency of 6 to 1 MHz. The power amplifier was excited by a carrier signal of frequency 900 MHz and modulated by a 3GPP WCDMA envelope signal having about 3.84 MHz of bandwidth. The data has been separated in extraction and validation to prevent any extrapolation problem. First, we use the extrapolation data to train our model, and the validation data to calculate the estimated output power. With these results, we compare the wanted output power with the squared output validation data. To the comparison, we are using the normalized mean square error, defined below, where n is the length of the vector, y_half is the vector of reference, in this case the wanted output power, and y_test is the vector that's been tested, the estimated output power. We simulated our model for different values of n, and got the results compiled in the table. We can notice that as m grows, the complexity of our model increases as well, and we expected to get a lower NMSE until we arrive at some limit. Based on the result, we assume that this limit is between m equals 2 and 3, because after that NMSE gets slowly smaller and does not compensate the needed extra time. Conclusion. Based on the report results of the simulation, we were able to validate our model and get an NMSE between -20 and -30 decibel, depending on the memory order. In general terms, we could say that if you need a model fast to simulate it, you can use m equals 2, and if you need a result with accuracy, m equals 3 should be better. Acknowledgment. We would like to acknowledge the financial support provided by CNPq as well Fundação Araucária. Here we have the list of references used in this article. Thanks for watching. If you have any questions, feel free to contact us by email.